Good morning, and welcome to the ATCO SpaceLab Speaker Series. My name is Kelsey Stephen, and I'm a member of ATCO's Transformation Team. I'm pleased to be your moderator today. I acknowledge the Indigenous peoples that are traditional custodians of the lands on which we work, live, and play today. While this is a virtual format, I ask that you join me for a moment of reflection on the meaning of place, to recognize the various traditional, ancestral, and unceded lands and their significance both historically and in our everyday lives. I do this to reaffirm my commitment and responsibility to improving my own understanding of Indigenous nations and to pay my respects to elders past and present in the communities and regions where ATCO operates. I am honored to live and work in Treaty 7, the traditional territories of the Blackfoot Confederacy, comprised of the Siksika, Kainai, and Piikani nations, the Tsuut'ina Nation, and the ATCO Stoney Nakoda, including the Chiniki, Bearspaw, and Goodstoney First Nations. This land is also home to the Northwest Métis and to the Otipemisiwak Métis government, Nose Hill Métis District 5, and Elbow Métis District 6. The city of Calgary is located where the Bow River meets the Elbow River, and this site has been called Mohkinstsis by the Blackfoot, Winchispa by the Nakota, and Gutitsi by the Tsuut'ina. Today's speaker joins us from Texas Tech University. I'd like to respectfully acknowledge the unceded traditional territories of the Comanche and Mescalero Apache peoples on which Texas Tech University is located. Today's lecture is a one-way video and audio format. Please ask questions by using the question icon on the right of your screen. We will open the question functionality shortly after starting today's lecture. I encourage everyone watching today to approach our time together with a growth mindset. Whether or not you're familiar with the subject matter, I know you will learn something new from this lecture. I will now hand it over to my colleague, Andrea Kleiber-Langen, to introduce our speaker.
Thank you, Kelsey. Welcome, everyone, and thank you for spending time with us today. We're thrilled to be joined by Dr. Dimitri Volchenkov, an accomplished professor of applied mathematics and statistics with Texas Tech University. Dr. Volchenkov has decades of international experience in complexity science, network theory, stochastic nonlinear dynamics, and data analysis. He is a former chair professor of risk prognostication at the Artificial Intelligence Key Laboratory at Sichuan University of Science and Engineering in China, a former research professor at the Bielefeld University in Germany, and former director of research at Le Centre de Physique Théorique in France. As an expert in complex systems and uncertainty dynamics, he has received many accolades throughout his career, including the G.M. Zaslavsky Award in Nonlinear Science and Complexity, a placement in the 1,000 Talents Plan program in China, the Humboldt and Volkswagen Research Fellowships in Germany, and the NATO and CNRS Fellowships in France. Today, Dr. Volchenkov will dive into the application of information graph theory, providing a framework for understanding the dynamics and interactions within complex networks. Information graph theory offers a novel approach distinct from geometric, combinatoric, algorithmic, and algebraic methods, emphasizing the evaluation of communication efficiency between system units over time. This methodology is particularly relevant for designing network on-chip architectures, engineering urban morphology, and developing smart city networks. Through examples such as urban pedestrian flows and city spatial organization, Dr. Volchenkov will demonstrate how information graph theory can identify patterns of isolation and integration, addressing the practical implications of these findings for architects, urban planners, engineers, and more. We are so very appreciative that you've joined us today, and we look forward to learning from you, Dr. Volchenkov. The floor is yours.
Dear colleagues, thank you for inviting me to participate in the ATCO lecture series. It's a great honor for me. I would like to express my gratitude to Professor Vakhtang Putkaradze for the invitation, to Kelsey Stephen and Alicia Trepak for organizing our meeting. My lecture is titled Navigating Complexity, information graph theory, and urban morphology. In my talk, I would like not only to discuss the analysis of urban networks, but also to engage the industry, you, in addressing important socio-economic issues of urban spatial organization. My work is broadly interdisciplinary. I apply methods from statistical physics, information theory, and nonlinear dynamics to model real-world systems. In 2008, I published a book on the mathematical analysis of urban spatial networks. I worked in this field for quite a time. I plan to tell you about the French architect Claude Nicolas Ledoux in his book L'architecture considérée sur le rapport de l'art, des mœurs et de la législation. I will discuss some ideas of space theory as well, whose best exponent was Sir Winston Churchill with his famous quote, "We shape our buildings, and afterwards our buildings shape us." I will also talk about thermodynamic approaches to urban theory. I understand how challenging it can be to listen to a mathematical lecture, so I have tried to make my presentation visually engaging and filled it with multiple examples, such as where the city of Lubbock ran off to, who makes the most money in Manhattan, how structural and social isolation are interconnected in German cities, what happened in the city of Regina, Saskatchewan, and more. In conclusion, I would like to draw your attention to the fact that modern cities are unprepared for three interrelated global cascading processes of our time: succession of states, urbanization, and human migrations. I will draw conclusions at the end of my talk. I begin my talk by discussing the fate of the once famous architect Claude Nicolas Ledoux, whose career was destroyed actually by the French Revolution. For subsequent generations in France, he became a symbol of le régime ancien. His buildings were ruthlessly destroyed in France, yet eagerly copied in Imperial Russia. In 1804, he published a collection of his work in a volume titled L'architecture considérée sur le rapport de l'art, des mœurs et de la législation. In his book, he came to the conviction that the revolutions are unnecessary if a city is properly planned and the built environment maintains morals, the economy, and laws in proper order. He dedicated the rest of his life to planning the ideal city in a circular form. His design was partially realized in the construction of the salt works at Chaux. However, in the middle of the project, the price of salt suddenly dropped. The funds run out. So only half of the city, a semicircle, was built. Meanwhile, urban unrest continued to shake Paris even after the French Revolution. In the 1860s, Emperor Napoleon III established a commission for the renovation of Paris. To facilitate the suppression of uprising, it was proposed to use artillery and cavalry to shoot down barricades with cannons and then disperse the rioters with a cavalry charge. The renovation of the city was entrusted to Baron Eugène Hauss-Haussmann, who laid out the urban fabric with 200 grand axes, creating a new urban organization in the form of a network of interconnected radial avenues. Surprisingly, uprisings in Paris ceased after that. Paris develops in a spiral. It grows with a new arrondissement. Maybe I can even use a laser pointer. It grows with new arrondissement like a large snail. After over a century and a half of development, the structure once created by Baron Haussmann had been engulfed by new urban development that has expanded far beyond the Boulevard Périphérique. Today, Paris has once again become a center of regular social clashes. Radially symmetric circular structures of urban settlements have been known since ancient times. Among them are old Baghdad and the ancient city of Ghor in Iran, the city of Palmanova in the Venetian Republic, and the modern Karlsruhe, the headquarters of Bundesverfassungsgericht, the Federal Court of Germany. The famous Commission of Three, convened in 1811 to discuss the development of New Amsterdam, New York, held a different opinion, being motivated by economic efficiency first, right-angled houses are the cheapest to build, as well as political acceptance, a democratic alternative to the royalist avenues of Baroque European cities. Urban greed was not a new term in urban planning indeed. The concept of the ideal city, Wangcheng, was developed during the Han Dynasty when Emperor Qin Huang unified the Chinese states. The 9x9 grid was based on the cosmological belief that the Earth is a square divided into 9 sectors, an extension of the 4 cardinal directions. This structure also resembled the magic square, a tool for divination. The design thus reflected the sovereign's influence and harmony over the various corners of a similarly gridded realm. The ideal city of the ideal ruler, Emperor Qin Shi Huang, Chang'an, the city of eternal peace, was well in accordance with the plan. However, it soon became clear that the ideal capital city had to be constantly relocated for various reasons. The grid structure was replicated several times, close to each other. The modern boundaries of the city of Xi'an are shown by the dashed line on this picture. A similar situation occurred with classical Roman cities, planned in the form of a rectangle composed of uniform blocks. The growth of such cities is accompanied by their constant movement. A European architect would say that built structures lacking of meaningful structural focus are doomed to wander. For example, the city of Lubbock in West Texas, from where I'm speaking to you now, had its boundaries defined by a belt road in 1960s. However, since then, passenger rail service had been discontinued. The train station, right here at the city center, historical city center, the train station lost its social role and the railroad became a barrier cutting off the northwest part of the city from the center and reducing its commercial and residential appeal. As a result, the city has spread southwest and since expanded beyond the Belt Road. Conviction in the mutual influence of built structure and quality of life has existed for many centuries. When in March 1941, the German Luftwaffe bombed the House of Commons in London, Sir Winston Churchill advocated for its reconstruction exactly as it was. He was not even deterred by the fact that the old chamber lacked sufficient seating for all its members. He believed that the structure, which did not accommodate everyone, was responsible for the democratic process and resilience of the British political system. We shape our buildings, and afterwards our buildings shape us. Indeed, the specific organization of built environments creates characteristic movement patterns within that reshape and edit social relationship between people, ultimately leading to the emergence of different personalities in them. This was vividly demonstrated in Berlin, a city once divided by a wall into East and West, which lived and developed according to different social principles in differently structured urban environments. being in the order, in the other sector, in another sector of the city, feels as physically uncomfortable. And perhaps there isn't a single political or social issue on which Ossi and Vessi share the same opinion. The clustered nature of poverty and wealth, as well as their surprising persistence in different neighborhoods of London, was described in the second half of the 19th century by the first sociologist, Charles Booth. Despite all the renovations, poor neighborhoods remained poor, and the people who settled there became impoverished soon. It created the impression that certain places in the city were literally cursed. Zoning is indeed observed in many aspects of urban life, such as the religious affiliation of residents, the crime situation, racial and ethnic composition of neighborhoods, and others. Zoning found its ultimate expression in the redlining policy. Redlining is the practice of denying people access to credit because of where they live, even if they personally are qualified for loans. Redlining initiates the process of urban decay, which quickly spreads beyond the boundaries of the affected area. An important contribution to the understanding of the significance of urban structure was made by Professor Bill Hiller of University College of London with his theory of space syntax. Perhaps his most famous book was Space is a Machine. According to the space syntax theory, a city converts a space pattern into a pattern of relationships. Cities generate more interactions with more people, producing denser patterns of connection as the grid constrains proximity. His success was due to the establishment of a business offering analysis and expertise in the built environment. The city was viewed by space syntax theorists as a network of vista spaces. The more visible a space is, the more attractive it is for people, and the better its socioeconomic conditions are. The firm offered services such as visual graph analysis, all lines analysis, through vision analysis, and agent-based modeling. And they priced between 40,000 to 60,000 pounds per square mile of urban development. Unfortunately, Bill had died in 2019 because of COVID, and apparently the business stopped operating. It must be noted that the simple equations of classical physics are inadequate for describing urban structure and its dynamics. Urban structure lacks Euclidean space. The network exhibits spatial inhomogeneity and anisotropy, a multiplicity of pathways, and dynamics that vary across different spatial and temporal scales. The traditional approach of using coupled differential equations is impractical, as simulated dynamic processes in networks often descend into chaos driven by numerical errors. The strategy for studying such systems was developed long ago in thermodynamics. Thermodynamics is based on the ergodic hypothesis. The time spent by a system in some region of phase space is proportional to the volume of this region, so that all accessible microstates are equiprobable over a long period of time. The ergodic hypothesis offers a solution to this dilemma by equating ensemble and time averages. It replaces the dynamic description of individual changes with a probabilistic description within the ensemble over an extended period of time, thereby circumventing the complexities of chaotic behavior. Switching between temporal and ensemble perspectives under the guidance of the ergodic hypothesis is a common approach in thermodynamics, equilibrium statistical mechanics, and dynamical systems theory. In the thermodynamic limit, where the number of particles becomes infinite and the volume unbounded at constant density, thermal fluctuations become negligible, and all thermodynamic quantities, such as pressure and energy, become straightforward functions of thermodynamic variables like temperature and density. Thermodynamics, which involves replacing actual microscopic dynamics with ensemble averages, resulting in description reduction, requires a thermodynamic limit. If put simply, something must be taken to infinity. When applied to networks, there are two possible thermodynamic transitions. First, infinitely growing graphs. So we send to infinity the size of the graph, which lead to the well-known theory of complex networks. And second, which we will discuss mostly in my lecture, dynamic complex network, where the graph remains finite. It doesn't grow. It may be even very small, like a small village. But the length of paths, walks in this graph, within the graph, tends toward infinity. I'm the author of the alternative approach to complex networks, which I have developed mostly in the context of urban networks. The initial application of thermodynamic approaches to networks emerged within complex network theory, nevertheless, where the thermodynamic limit of infinite graphs was considered, rendering graph structural fluctuations negligible. A key focus of their discourse was the universality and ubiquity of the scale-free graphs, which were found to be prevalent across various domains. These graphs grew according to the preferential attachment mechanism, often referred to the Matthew as the Matthew principle, encapsulating the idea that rich get richer. Indeed, if we assume that new nodes preferentially connect to those with higher degrees and in proportion to the exponential factor termed fitness, then the distribution of links among nodes with a given energy or attractivity epsilon adheres to the familiar Bose-Einstein statistics. As a result, they observed the Bose-Einstein condensation in networks. The fittest node gets the most edges. You remember this naive interpretation of natural selection in the theory of evolution by Herbert Spencer. Fittest survives. That is. Nowadays, we understand that complex network theory is of a limited relevance to real-world networks. Firstly, an infinite preferential attachment graph forms a scale-free tree devoid of cycles, where cycles are essential for feedback mechanisms crucial to the proper functioning of many real-world networks. Second, most real-world networks are finite and often quite small, with structures meticulously shaped by their functions, far from being random. Finally, from the network evolution perspective, Bose-Einstein condensation, when fittest survives, corresponds to stabilizing selection featuring nodes of high centrality or fitness. The simplistic stabilizing selection approach in complex network theory overlooked the crucial disruptive selection mechanism that fosters innovations and novelty everywhere. In the thermodynamic limit of infinite walks, the thermodynamic quantities of a graph represented by its adjacency matrix. Adjacency matrix is a matrix which has of zeros and ones. It has one if the pair of nodes are connected within the graph, and zero is zero otherwise. And since it's a simple matrix, we can use the eigenvalue decomposition, calculate its eigenvalues and eigenvectors. So the largest eigenvalue alpha max, it's a maximum eigenvalue of the adjacency matrix A, and the the corresponding eigenvector belonging to this eigenvalue is called the eigenvector centrality of the graph. So all quantities such as the exponential growth rate of graph free energy, the number of different paths available in the graph, and other functions may be calculated only in the thermodynamic limit, only with the use of the alpha max, the maximum eigenvalue, and the eigenvector centrality corresponding eigenvector. This growth rate, for instance, is known as graph topological entropy, the space dimension analog in the graph. Missing nodes and edges may dramatically reduce the graph free energy, reshaping the global mobility patterns in that. As shown on the left-hand side simulation in the city graph of New York, a single missing node affects many paths, resulting in an increment of free energy by the amount of entropic pressure. Similarly, we can introduce entropic force, a directional analog. If a traffic congestion deadly blocks a street, as seen on the right-hand side here, the traffic jam may propagate further, immobilizing transportation in the entire network. We highlighted the values of entropic pressure and force in the city graph of Lubbock, the home of Texas Tech University, taken from the OpenStreetMap service. The value of entropic pressure in this spatial graph of Lubbock attains maximum at the contemporary structural focus of the city, far apart from the city historical downtown. The nodes of the city spatial graph on the right-hand side are highlighted according to elements of the Fiedler eigenvector belonging to the second largest eigenvalue of the entropic force matrix, indicating the direction of the fastest decrease of entropic force over the city spatial graph of Lubbock. The entries of the Fiedler eigenvector are zero everywhere except for a narrow band extended from the historical city center here. It's a railway station, former railway station, toward the contemporary structural focus of the city, highlighting the process of urban decay. The structural focus of the city absorbs very long walks, while the historical center, anchored at the abolished city railway station, expels long walks. Also, railway construction enhanced the city status of Lubbock in early days. Its maintenance has a continuing negative impact on the urban development, since railways barricade streets, dramatically cutting down the number of possible paths people can drive or walk, and create isolated neighborhoods here. As a result, Lubbock grows to the southwest, running away from Loop 289 that marked the old city boundaries in the 60s. Let me remind you that in statistical mechanics, a canonical ensemble refers to a set of system states that can be characterized by a stationary distribution. Even though the system is in constant motion, the density of states for such ensembles remains unchanged. Canonical ensembles of walks consist of various types of random walks defined on the graph. There are infinitely many types of random walks. The most well-known are isotropic random walks, where a walker at a given vertex chooses the next vertex to visit uniformly at random from all accessible neighboring nodes. In other types of random walks, the traveler selects among paths of length 2, 3, and so on with equal probability. Vertices that provide access to the greatest number of longer paths are favored. These random walks are anisotropic. Finally, in the limit, we arrive at so-called the Reuel-Bowen random walks, where all infinitely long paths starting from a given vertex are chosen with equal probability. These walks exhibit the highest degree of anisotropy. Each type of random walk corresponds to its own stationary distribution, which defines a specific measure of centrality, indicating the importance of a vertex for the given walks in the graph. Different types of random walks indeed exhibit striking differences. Imagine dropping a bead of blue ink and red ink and letting them spread according to isotropic diffusion on the left and Reuel-Bowen as an anisotropic random walks on the right. While the blue ink slowly and evenly fills the available space, the red ink quickly leaps to the most open area of the environment and then remains there forever. It appears as though the behavior of the red ink exhibits some form of intelligence. even it is also a random walk. Why are random walks of interest to us? First, because they allow us to measure distances on graphs. Indeed, the conventional distance on a graph defined as the shortest path between vertices. And it may be relevant for many practical applications. It's often more useful to employ something akin to path integrals, which physicists favor. Every possible path between two vertices is accounted for, though some paths may be chosen more frequently than others. The key is to eliminate loops from random walks and ensure that the random walks are self-avoiding. Otherwise, one could wander in a maze of streets endlessly. Imagine we have collected all the travel logs from every traveler who has ever been in the city. Each traveler started from a randomly chosen location, X0, recorded the sequence of streets and places they visited. And in this case, the location I in the city can be characterized by the expected first arrival time in these logs. The first passage time here, so the expected time that then we meet I for the visit I for the first time, refers to how many steps a random traveler needs in average to reach a particular place for the first time. To measure the distance between two landmarks, we calculate the average time it takes for a traveler to move from I to J for the first time, and then return to I for the first time as well. This is known as the commute time, so we commute between I and J. What is truly remarkable is that the first passage time and the commute time are related by Euclidean space laws. Random walks effectively restore, yet in probabilistic sense, the Pythagorean theorem, though in the realm of probabilities, right? While in the real space, it did not exist. You might ask me, so what actually do random walks have to do with anything in urban planning in cities? Every morning I travel to the university and my road is anything but random. What do random walks have to do with human behavior in an urban environment? My response is that psychologists believe that Euclidean geometry is wired in our brains. As such, random walks and their associated probabilistic Euclidean geometry of networks shape our perception of these environments. Can we observe the first passage times in real life in cities? Absolutely. Each location in the city has its own first passage time, which we can calculate from a map. The farther I travel, in a probabilistic sense, right? In the sense of accessibility, the more intimidating the buildings around me seem. As for all data, the rather amusing prices from 2005, right? Each random step costs $120,000 per square foot. I mean, tax assessment value of the property. I believe that mathematics is a cognitive science ultimately. We study the way our minds work. That's what we are doing. Therefore, mathematics could and should have a tangible impact on quality of life, economic development, and the welfare of society. Cities are graphs in which some places are easily accessible, others are not. Well-accessible places are more favorable to the public, while isolated places are either abandoned or socially misused. In a long-term perspective, inequality in accessibility results in disparity of land prices and in social inequality. Many neighborhoods are cut off from other parts of the city by poor transport links and haphazard urban planning, which can often lead to social ills. Our transportation metric helps to spot hidden areas of a geographical isolation in the urban landscape. People are not random walkers indeed. However, they used to live in Euclidean space and they form a Euclidean mental model of any urban environment by learning it. Isolation cartography would display not only the relative land price, but also figure out the annual number of criminal reports, prison expenditures, annual income of inhabitants, and other socially relevant variables. A great amount of money had recently been invested in Manhattan after the terrorist attacks. Also, the global structure of urban fabric has not been changed. My bet is that the microscopic social situation would return in due time, as it has already happened many times in Manhattan's history. How was the annual income of Manhattan homeowners distributed in 2005? Based on the isolation, probabilistic isolation of their residences. Here is how. The wealthiest individuals lived in areas with the best accessibility, while those in the slums would fare better in prison, as conditions there were actually more favorable than their actually life conditions. Urban structures determine not only our present social and economic well-being, but for those generations to come. Isolation cartography helps us to identify the locations of former ghettos many centuries after they had been closed. The Ghetto Vecchio, the old Jewish ghetto of Venice, is the perfect example, is the most isolated part of the city. When traveling by train across Germany, we consistently observe one thing. Mosques are located right next to the railway tracks, while churches, German churches, are situated far from them at the city center. What's going on here? The issue is that railways cut through street networks, creating isolated pockets of land. Land prices in these areas drop. Minorities purchase the land and build mosques there. Let's look at the map. A church has an isolation level of 3 decibel here. I mean, there is isolation with respect to the entire city structure. While a mosque located next to the railway has an isolation level of 12 decibel. This illustrates the ultimate connection between social and structural isolation. They also go in parallel. And this is how the multicultural European project has failed. Shortly after the publication of my book, Mathematical Analysis of Urban Spatial Networks, I was contacted by the city administration of Regina, Saskatchewan. They had a railway yard right in the heart of the city and decided to revamp it. A very ambitious and expensive project. During the construction work, the central part of the city was blocked, disrupting transportation between the city center and the suburbs. Riots immediately erupted. The city administration labeled these riots as racially motivated, suggesting there were issues with racial hatred. In reality, there were nothing racial about it. The problem was that minority residents lived in the most affordable and isolated areas, the suburbs, which lacked reliable transportation links, and that they became the primary victims of the renovation. Probabilistic geometry of canonical ensembles of blocks, the first passage times, may be used to quantify the isolation and integration in city graphs. That is important for urban sociology. Sociologists think that isolation of city neighborhoods fosters poverty and crime in their dwellers. The first passage time quantities, the global connectedness of a node with respect to the entire graph structure as considering all possible paths to the node available in the graph. Also, some paths may be more probable than others. Computed isolation aligns well with how people perceive isolation in their everyday experience. In our recent study, we found a close correspondence between the calculated values of isolation index for the Texas Tech University campus and isolation perceived by human subjects as reported by students and faculty in our longitudinal survey. In the heat map shown in the right-hand side picture, we have shown the kernel density of the reports, indicating the place in the campus as being relatively isolated. We can introduce the isolation and integration indices of the places as normalized first passage times to nodes measured in the decibel scale. The degree of isolation is assessed by first passage times calculated for the isotropic random walks here that are insensitive to the structural heterogeneity, defects, and boundaries of a graph. On the left-hand side, we have highlighted the isolated regions of the city graph of Lubbock. The central regions of the city encircled by the belt road have a relatively good connection, except for the northeast part of the city cut off by railways. The degree of integration is assessed using the Reuel-Bowen anisotropic random walks based on the intuition that areas and places of motion well integrated into the urban fabric should belong to the most possible infinite walls existing in the graph and therefore determine the dominant mobility pattern in the transportation network. On the right-hand side, we have shown the integration index in the city of Lubbock. Places hosting the lion's share of very long walks, they are hot here. Long walks highlighted hot, they feature the global mobility patterns in the urban structure of Lubbock. Also located within the historic city borders, areas such as those on the northeastern portion of the city that are shut off from the center by the commercial trains, significantly reducing the number of infinite long pathways, are only sporadically incorporated into the city fabric. Due to the structural imbalance fostered by railways, relatively isolated sprawling areas of the Southwest can statistically accumulate the bulk of possible infinite roads here. And move Lubbock's mobility patterns from the historic core to the southwest suburbs. Integrated isolation is not an oxymoron. Here you see that some places are isolated, but and as well integrated as well. These are home for the wealthiest people in our town. On the contrary, the northeastern portions, not isolated and not integrated of Lubbock, cut off by railways and characterized by very low dark blue values of the integration index, aligned with the historical segregation patterns of spatial and land division formed earlier in the 20th century. These are areas where Black and Latino workers were settled in labor camps. It's also interesting to compare the map of city integration in Lubbock with the map of daily crime incidents. The fewer infinitely long path a place hosts, the more police calls you can expect from there. Another crucial area where random walks can be valuable is navigation. How accurately can we predict the position of a traveler in an urban network if we know they were once seen at a specific location? And does the traveler themselves understand where they are now? The answer, of course, depends upon the strategy of the walk. What do I mean? Let's consider the classic example of coin tossing. So coin tossing, right? So we have a simple logic scheme here, head, tails, and the probabilities of switching between these states. When I flip a coin and catch it, I gain exactly one bit of information, head or tail. This is one bit of information. Even if the coin is biased, with the heads or tails appearing with some probability P, each flip still provides precisely one bit of information to me. However, if the probability of repeating site P is 0, I can easily predict the outcome of the next coin toss. It will alternate constantly 0, 1, 0, 1, 0, 1. Similarly, if P is equal to 1, then states repeat itself 0, 0, 0 or 1, 1, 1. So everything is clear to me. One bit of information, but I can predict everything. But if I were tossing a fair coin with P equals 1/2, I would be unable to predict the outcome. Thus, knowing the history of previous tosses allows me to attempt to focus the result of the next one. Furthermore, if the probabilities of repeating sites are close to 0 or to 1, I can attempt to predict the outcome of the next coin toss simply by knowing the current state, current result of tossing. If the probability of repeating state P is close to 0, I would expect the current symbol to be repeated. Conversely, if the probability of repeating state P is close to 1, I would predict the symbol to change it to its opposite. However, only with a fair coin, where both outcomes, repeat or alternate, are equally likely, do I face uncertainty because my predictions contradict each other. The remaining part of the bit, shaded in purple, remains unpredictable. It represents an information component existing only in the present moment, not influenced by the past, nor affecting the future. And I can apply the same concept of information decomposition to city structures if I understand the strategy of random walks. So I play in coin tossing with cities. Frequently visited sites are better predicted than those that are little frequented, especially in the long run. The more frequent a node, the more predictable the navigator's position visiting it. The degree of uncertainty of a current position of a walker in the graph is assessed by the walk's entropy. Walk's entropy that can be represented as a sum of predictable and unpredictable information components, precisely like we did it with coin tossing. Namely, the very first term here in this decomposition represents the excess entropy, the information efficacy of the path integration strategy, taking the entire walk history into account. The second term describes the efficacy of landmark-based piloting that uses the present location of the navigator to predict her forthcoming position. The remaining part assess the true uncertainty about the future state of the chain that cannot be resolved neither by observing the history nor from knowing the particular landmark where I'm located, place where I'm located for the moment. The predictable and unpredictable information components have the same structure as the entropy, right? So it's just the same structure. So we can introduce navigability potential and strive potential to the node. So phi and psi. One, navigability potential characterizes the degree of navigability to a node. Another characterizes the strive this node has in the graph. The navigability score quantifies a chance that a node may be a precursor to visiting other nodes in the graph. The striving potential of a node quantifies its neighborhood exploration time. Indeed, the ability to navigate in a graph heavily depends on the strategy of random walks. Navigability under isotropic walks in membrane, shown in this picture, is based on the boundaries, while for the anisotropic walks, in which all infinitely long walks are taken equiprobably, navigability is based at the center of the graph. As such, the walks are statistically confined there. In our longitudinal survey about walkability of the Texas Tech University campus, we found that the calculated navigability scores are closely related to the places reported by students and faculty as being interesting, secure, and pleasant to walk. The corresponding density kernel map of subjects reports is shown on the right-hand side. Confusing environments are not associated with safety, as they can significantly increase the risk of accidents for pedestrians, as they may struggle to navigate safely and make appropriate decisions while crossing streets, interacting with traffic. The only mismatch between the navigability scores calculated in campus and walkability assessments reported by human subjects was found in young male students considering this sport facility as an interesting zone to walk. Finally, let's discuss the problems of random modifications and transportations in networks. Here we introduce the grand canonical ensembles of walks. Let me remind you that the grand canonical ensemble represents the possible states of a system exchanging energy and particles with the heat bath in thermodynamic equilibrium. The graph is considered open to modifications that are taken with a probability proportional to the exponential factor termed as fugacity. The main question we need to answer here is where, in which location, is the next city renovation most likely to occur? How easily can a given place be detached from the urban fabric? This question is addressed by fugacity, a measure that characterizes the proportion of infinitely long path hosted by a given vertex in the urban graph. The fewer long paths dependent on a given vertex, the easier it is to detach or modify it. Fugacity describes the change to the system of long walks due to adding or removing a node. In the thermodynamic limit of infinitely long walks, fugacity is nothing but the inverse eigenvector centrality of a node. The nodes of high eigenvector centrality share many very long paths and therefore are characterized by the low fugacity scores, and vice versa. The graph vertices with the inferior growth rate of infinitely long walks appear to be insufficiently integrated into the graph structure, and therefore they might be lost. The graph nodes located at the corners of the membrane are easiest to remove, as this will affect the minimum number of long paths in the graph. Where the central graph most likely to start growing in the future? At those very same corners. This is why cities organized as rectangular grids of uniform blocks tend to sprawl outward, like Lubbock or the ideal city of Emperor Sinchuan. Different vertices in the urban graphs host varying proportions of very long path, and the likelihood of renovating of these locations differs accordingly. I readily acknowledge that this principle did not work for the city administration of Regina in Saskatchewan. They began the renovation strictly contrary to this principle, creating more problems in more central vertices of the urban graph. The distribution of fugacity across the graph's vertices follows a Fermi-Dirac distribution, which is unusual for non-quantum physics problems. Interestingly, the same Fermi-Dirac distribution involving fugacity also appears as the unique stationary solution of a Fokker-Planck equation describing the continuous time dynamics of distributions under the noisy transportation capacity of random edge rewiring in a graph. If we add the Wiener process of strands beta to the forward Kolmogorov equation, we get the Fokker-Planck equation preserving the form of Kolmogorov equation. And the derived Fokker-Planck equation has the Gibbs distribution as its unique stationary solution, taking the form of Fermi-Dirac distribution of fugacity if beta equals 1. In general, the Fermi-Dirac distribution depends on beta, and in case of very strong noise, then graph is permanently rewiring. Then the station distribution converges to a uniform distribution over graph's nodes, independently of the graph structure. Indeed, in this case, the traffic may get stacked everywhere. In transportation problems, we observe the typical stochastic resonance. While central hubs accumulate the most of traffic in normally operating transport networks, As it is shown in the traffic congestion modeling on the left-hand side graph, traffic congestion may catch at the nodes of low centrality and structural bottlenecks due to the random fluctuations of the transportation capacity in networks, as it's shown on the right-hand side graph. So this is the core and the periphery of the graph. They all flip in case of noise of the transportation capacity, some rewirings or so. Okay, enough maths. Let's pose la question dans la vie. We are witnessing presently 3 interlinked chain processes occurring in parallel. The fragmentation of nation states, urbanization, and human migration. These processes did not begin yesterday or even in this century or in the past century. They have been unfolding for a very long time. In 1800, there were only 22 states in the world, empires dividing the globe. Today, there are 206 states. Just checked on the Google. When I wrote my book, Survival Under Uncertainty, from where this picture had been taken, there were only 197. If you plot the number of states over time, the curve resembles an exponential function. Nation states behave like radioactive atoms. The more they are, the faster they decay. The average lifespan of a state is 122 years, with a half-life of 84.5 years. By the end of the century, half of the current states will have vanished from the map. This process is random. We can't predict which state will collapse next. Currently, more than half of humanity lives in cities. The urban environment has become the primary habitat for us. Larger metropolises grow rapidly, while smaller towns wither and disappear. In Russia, 36,000 settlements have vanished over the past 30 years. In China, 20% of cities have disappeared in the same period of time. However, the population of remaining 106 cities of the remaining 687 cities in China has exceeded already 1 million people. Gigantic metropolitan agglomerations have emerged, such as in the Chongqing area, about 64 million people, and around Shanghai, about 110 million people. Migration volumes are continually increasing as well, a chain process in itself. Each migrant leads to the arrival of 2 to 4 new migrants. Migrants don't settle in rural areas, nor in small cities, but they go to large cities where they have better chances to get a job. These processes are closely interconnected and accompanied by the destruction and simplification of urban environments. Old, complex urban structures are dismantled through wars, state secession, right? Or creative destruction, while new homogeneous developments are rapidly constructed in other areas. This is Houston. Typically cheap and uniform, located along roads in suburban areas. They are sprawling. This type of development is more rural than urban. Wars force people to migrate on a large scale, and expanding cities with inexpensive developments attract these migrants. A significant role in the destruction of vibrant urban environments is played by urban sprawl. The expansion of uniform development areas shift the structural focus. It is an example of Lubbock. Focus of the urban environment away from the center, triggering process of urban decay and disintegration in the former center. And that is how Detroit met its downfall. On one hand, the city is unprepared to accommodate and integrate millions of migrants from rural areas and other countries. In New York, they are currently housed in hotels in the city center. There is little space available, and the city administration has even less money to accommodate the migrants. On the other hand, The arriving migrants are not ready to live in an urban environment that is organized differently from their familiar surroundings. This initiates a process of urban decay. The city becomes a center of suffering and the focal point of resentment for both newcomers and long-time residents. On a smaller scale, we have already observed these processes in Europe during the first half of the 20th century. I mean the chain reaction of collapsing states and the century-long regimes of political governing, explosive urbanization, and the avalanche-like growth of human migrations. The inability of cities to accommodate hundreds of millions of newcomers triggered the processes of urban decay and gave life to ideologies of urban disintegration. These urban decay ideologies view the city not as a land of opportunities, but as an ecosystem with scarce resources. Survival in the hostile environment of a dying city was preached through the lens of social Darwinism, and the decline in birth rates was encouraged. Today, ideologies of urban decay get new life, indicating the forthcoming social collapse. Europe paid a steep price for urbanization in the last century by moving 200 million people into cities. It lost over 200 million residents to wars, political repression, disease, and famine, with many scattering across the globe, including to Canada. The relentless wars continued until the cities, which had become epicenters of human suffering, were entirely devastated. Only then did the chance arise to rebuild them from scratch following new plans. Are we on the brink of another such war? Mirabile futurum, ne esto mihi durum. A wonderful future. Don't be hard on me. This is the first line of a well-known children's song in the Soviet Union from several years before its collapse. Oh, what to take home? Revolutions are unnecessary if a city is properly planned and the built environment supports moral, the economy, and laws in order. The built environment recreates long-lasting patterns of social relations and economic behavior, solidifies them for the generations to come. Renovating individual neighborhoods without fundamentally changing the entire network structure is pointless. Wasted resources and means. The network will reclaim its course and reverse everything back. Modern cities are not prepared to accommodate millions, and migrants are not ready to live in decaying cities. The structural and cultural conflict is fraught with deep social and political upheavals, examples of which we can find in the past century. Thank you very much for your attention. I stop sharing my screen and ready to answer your questions. Thank you.
Thank you very much, Dr. Volchenkov. That was a wonderful lecture. We're now going to move into our question and answer period. So for those that have joined us online, feel free to look at the top bar along your screen, and there is a Q&A function where you can ask your questions. Give any questions in the chat a thumbs up to upvote them, and I will try to get to as many of them as I can. Our first question today comes from Scott Mahan. And Scott asks, has this dynamic model been applied to utility transmission distribution networks where there are multiple usage destinations as well as limits, supply inputs, and several interconnection points? He asks, as you showed the traffic disruption model of New York City.
Well, indeed, we can use different, you remember I introduced different random walks. Each random walks has its own scale, right? So the idea is that we can model utilities and different transportation modes using different scales. Yes, a city is a multi-level entity, multi-level multi-level system, and indeed it could be characterized by many scales, spatial scales and temporal scales. And what I propose with this random box is a kind of scaffolding system. Scaffolding, just a description of the system at different levels. Well, indeed, some real problems related to transportation, different modes. If we would have some projects related to that, because it's a mathematic method. Well, we can apply, we can work out. For the moment, what I did, I worked on the basic principles. I work on basic transportation modes. I mean, on the city graph, basically, right? What we could get from the OpenStreetMap. We just download these maps. We created the graph, and we work out some basic principles. If we would know more, we could say more. So this is my answer. Yeah, it could be done. Everything could be done, right? Indeed, calculate. We know how to do it.
Yeah, that's wonderful. Yes. Thank you. We will go to the next question here, who comes from Richard Brewell. Richard says, such an interesting topic. Is there any allowance in these formulas that account for the class systems which still exist in many countries today? Many thanks.
I worked with, while in Germany. I'm German, so I worked in some social issues in this related to these problems. In particular, people of different classes and different ages. They have different mobility. Renters, pensioners have low mobility. Kids have high mobility. People, jobless people have low mobility. Well, how did we model it? We simply assign some weighted probability distributions, because, for instance, we know how many people are jobless in a particular neighborhood, how many pensioners live there, how many kids, right? So we can start our study from different distributions. Okay, we have 20% of kids, we have 30% of, 20% of pensioners, 60% of working people, say 30% of them have no job. We can model mobility patterns and the right distributions for them. We use this strategy to, I wish, I may show these pictures, but in the particular neighborhoods, we developed sport facilities where people could jogging, where they could practice sport. Where should we put sport facilities for them? Indeed, who would make sport? Not pensioners, but maybe kids, right? Maybe some people who have time. And we should make this path, where to put these facilities, considering that, we address these facilities to a particular category. Yes, it's a long walk, it's a hard work, but, using some hypothesis about and knowing the data, what is the share of pensioners, for instance, or kids in or maybe classes, if we talk about social classes, what do we know about them? Okay, if we learn about what could we expect from them, we could adopt our networks and the urban environments toward their needs, to meet their needs. Okay, thank you.
Yeah, that's wonderful. Thank you. And I think it's really important what you pointed out about the fact that this is also an accessibility issue. It's important to consider, can people get to where you're building these new complexes? So thank you for that answer. That's great. This next question comes from Patrick de Niverville. Patrick asks, how do we determine which parts of a city, like the examples you showed with the city maps, are suffering from urban decay, and can it be measured?
So what we actually did, what I did, first of all, I remove a node. I remove this place from this urban network, from this urban fabric. What would happen? Okay, so this is a pressure. Now, I can remove an edge, some transportation road. what would happen to the network? What we used, it's a Fiedler vector, second eigenvector, in this entropic force matrix. Entropic force tells me how the mobility pattern would change, would move if I remove a particular transport connection. And then it appears that what it gives to me. This is a Fiedler vector almost everywhere at zero. Is zero excepting for the places so one center attract all long paths, another places repel it. Repelling places correspond, I mean, you remember this yellow tail after the kind of a block, I would say it's kind of a comet, right? So the black center of structural focus of the city, and then a yellow tail. Yellow tail is an urban decay. There are hundreds of homeless people there. Right now, it's not that far from me. Why? City is dying there. Why? Because well, they stopped these railway connections in 70s because they believed they could use these cars everywhere. We are located, say, about 6 hours from the New York City. But this railway station it was designed to be a center of the city. Now it is not. And then close to this region, we have a dying environment who had once been developed to serve people arriving at the city. Now it's dying. It's just homeless people, just squats, whatever. You know, I can't let my children go there. Okay, so this is and it's visible. It could be calculated. We can assess the degree of this decay, how it would evolve in the future, what would happen next. In principle, we can prevent it, yes. If we remove the industrial trails out of the city, I'm sorry for being canoic. I already explained it many times to our city administration, but it's too expensive. But if it's not it doesn't have a social role anymore, it should be out of the city where the entire industry is. But okay, thank you so much. Great question. Thank you.
Yeah, thank you for that answer, Dr. Volchenkov. And you already partially answered this follow-up question from Scott, who asks, could this urban decay be predicted from past patterns and future planning to see how decay could spread and how it could be reversed?
Well, exactly. It could. Well, actually, what I think, there should be an expertise before any renovation, redevelopment, or whatever. There should be an expertise because each renovation nowadays is very local. They decide to construct a new building or a new neighborhood somewhere. How this construction or a bridge, say, or a highway, how would this change affect the entire network? In Stuttgart, they constructed a new highway to the airport, and the entire city stopped. On one hand, superficially, it's a new connection. Everything should go smooth, and the transportation in the city may be improved, and the transportation to the airport. But in reality, it happened the reverse because traffic in the particular roads, traffic of cars and vehicles toward the airport blocked. It's called Stuttgart paradox. Blocked the traffic in the entire city. Indeed, there should be an expertise. Each and every, I mean, and what could we do with how to prevent it? well, indeed, we should make a mathematical modeling, I mean, on the level of the city structure, how to avoid such problems, because it's computable. And in particular, well, there should be expertise. We should, and moreover, you know, there's this case of our city when we don't have a socially relevant railway service, but this railway is still in the city. It's something alien to us. And then it blocks streets. It creates isolated pockets. It makes prices go down. It makes this ghettos on this northeastern part. But you know, it's completely visible, right? I can draw it, and everyone can draw it. You can draw it. You can understand what would happen if we do something. So each decision should have an expertise before we invest huge amount of money. Yeah, thank you so much. Yeah, thank you. Very great question.
Thank you. Yeah, that's awesome. And we have one last follow-up question here about urban decay. Richard asks, how could we govern cities differently to stop this decay if we are able to predict it?
Well, as I wrote in the conclusion, the entire city structure should be rethought and redeveloped. The entire city structure. Why we have wars? I don't believe in politics, sorry. I don't believe in economy, sorry. I believe that it is because cities became the epicenters of suffering. We don't have, the only way how to redevelop a city nowadays is to bomb it out and construct a new. In the 20th century, we bombed out Germany to the ground. And then we made a locomotive of European economy. Everything had been redeveloped anew from scratch, according to the new plans. You know, in Venice, once upon a time, well, if you visit churches, and then they will tell you a story. Okay, unfortunately, a new artist could paint, make pictures or whatever in churches only if a church was burned out. So they regularly burned churches. It was the meaning of wars on European continent. They destroyed their cities. Americans use another strategy. They move their cities run away, right? And redevelop all the time anew. Is it reasonable? Is it wise? What to do with Detroit now? They pour money again. Okay, it's an, you know, Abbey. I mean, it's just, you can pour as much money as you want, as you can, but the system would play back. It will be still, I mean, problematic reason, but you know, at least we now have kind of ability to see it, how to prevent, how to redevelop it. Maybe let's do it in an intelligent way, not destroying the entire city. Well, I'm just thinking, I was born in St. Petersburg. If it would be destroyed, you know, well, it will be a pity. Okay, so thank you so much. This is a great question as well. Yeah, thank you.
Thank you. Yeah, that was great what you said. I think the message I took away is that we can learn from past mistakes in history to do better in the future. So thank you very much.
Thank you.
Our next question comes from Alicia Tropak. Alicia says, thank you for highlighting the problem we are facing, as well as the opportunity. Based on your research and observations, what should city planners start doing today that they are not doing yet?
First of all, they should download the maps of their own cities from the OpenStreetMap, so OpenStreetMap project. It's a non-commercial project. You can download the real city maps then they should be able to analyze it and change their policies before redevelopments, investments, or whatever they want to do. First, check how this redevelopment would affect the entire city structure, because it might create the regions of poverty, isolation, some, islands of isolation, where the city would go downhill. You make it intelligent planning, right? And therefore, we need industry, because what could I say? For 15 years or even longer, I attend different conferences, city councils, trying to explain what's going on, what would happen after the next redevelopment they plan. But okay, I feel myself like a Don Quixote of Cervantes. I'm explaining the situation, but industry doesn't know about me, doesn't know about the problem. And therefore I'm here now, right? Just to open your eyes, open your mind. We should think first before invest money, because cities is a system which work and affect interactions and social interactions in life, not only our life, present generation, but those generations to come. We should be responsible before our kids. Without that, there might be catastrophe, because nowadays we can change or redevelop a city only by destroying it. But many people die. We have a lot of migrants. Now urbanization occurs in Africa, in Asia, and we have tens of millions of migrants. They will destroy their cities in wars soon. And what we will do with this 100 million people that would come to us? What we will do? What Trump proposed to deport 40 million from the United States, how would they do that? I don't know. Okay, I'm not a lefty individual, believe me, but I don't know how to do it. Maybe we could start thinking first, redeveloping our own environment. This is our ecosystem now. Cities are our major ecosystem now. Let's think about how it works. So make an expertise first. And this is a great business. Nowadays, no one actually, before there was Bill Hiller in London. They tried at least to assess it using Vista spaces. Now no one does it. If industry would be interested in such kind of projects, this is a huge industry. Redeveloping all cities in the world. It's amazing. Okay, thank you so much. And I'm really open to any interactions in this direction. I feel myself like a monk on a mission. It's really important. War would come soon to redevelop our cities.
Thank you very much for your insights. That was great. I think what you emphasized that's really important is that it's going to take a lot of different groups working together to make a difference. So especially those in industry will have to really start considering this problem on a deeper level. Our next question here comes from Robert McDonald, and this will be our second last question as we're almost at time for today. So Robert asks, are the edges in your network weighted by distance, by travel time, or by something else?
You know that what mathematically, this is a linear algebra. I don't have edges. I calculate the distributions are calculated using basically, it's a random walks, right? In school we studied random walk, it's a Markov chain, it's a matrix. zero, I mean, of some numbers, probabilities summing to 1. It's a stochastic matrix. What I'm doing, I'm working with this matrix. I don't model anything. Modeling takes hours, years, or whatever, and the outcome is not clear. Why I'm using this random walks, because we can calculate processes on in each scale, spatial temporal scale separately. We can understand what's going on at different scales, what may happen at different transportation modes. We don't model. Okay, it's a simply matrices. Okay, so this is a maybe. If you have questions, you always have my email. You can, if you have questions, guys, please don't hesitate to write me an email. Don't hesitate to give me a call. All data is open, so I mean, all my. I'm really happy to talk to you and to discuss whatever might be interesting for your work. Thank you.
That's great. Yeah, thank you for that clarification, Dr. Volchenkov. And so our last question for today comes again from Richard. And Richard asks, does particular culture affect these models, especially with the traffic jam model? I have noticed that traffic works better in less developed countries as opposed to developed ones. I found mutual respect plays a big role in traffic congestion.
Yes, I draw in China and in Germany and the United States. These are different worlds. Yes, indeed. Indeed, for many reasons. And it's true not only in relation to traffic, but in all aspects of our life. People consider each other differently because they grow in different built environments. In the Soviet built environment, in Eastern Germany, or in Russia or elsewhere, people interact with each other differently. They consider themselves because well, they grown for you remember, I mean, this Eastern Germany and or Moscow and these huge avenues, amazing avenues. You don't have connection to others. We are far from each other. We were far from each other. In Western world, people get closer, right? They interact differently. They may respect each other to a higher degree, right? Well, if it's allowed to say. People are different because they grown in different ecosystems. Yes, it affects traffic, it affects social life, it affects violence, crime, you know. Just to note, many, many things. And this is a problem of migration as well, because these people arrive from different, and it takes years, decades to get adopted to different cultures, to get adopted to different, and indeed it depends upon the education, whatever. It's a very complicated system. As since it's complicated, it's unstable. And this is very dangerous. Finally. Thank you so much, yeah.
Thank you very much, Dr. Volchenkov, for all of your insightful answers and for your engaging lecture today. I want to send a special thank you to everyone who joined us online, and a very big thank you to everyone on the transformation team who helped make this event possible. If you enjoyed this lecture today, we are going to have another lecture on September 26th, so make sure you stay tuned for the details. And thank you very much, everyone. Enjoy the rest of your day.